to make a few comments on the properties of real number operations. This is a table from your textbook. I've pulled this from section 5.5, and this is page 262. Alright, so we have a list here of all of the different properties. There will be a video that follows this one that talks about the closure properties, not only for real numbers and addition and multiplication, but also other types of numbers and other operations. So I wanted to point out a few things. First of all, when we talk about these properties, we always talk about them in the context of a set of numbers and a particular operation. So in this section, they haven't mentioned a set of numbers along with each property because they've mentioned that in the header for this table. So we're only talking about real numbers for this table. And then we also have to specify an operation. So, for example, we see commutative property of addition or commutative property of multiplication. Now that's really important because only certain operations have those properties. Now you'll notice they did not mention a commutative property of, say, subtraction. And the reason is that subtraction is not commutative for real numbers. Or in other words, something like 3 minus 1 is not the same thing as 1 minus 3. Alright, so that's why it's important to mention those two things. Another question that students commonly ask is, how do you keep all of these properties straight? This looks like a big list. How do we know which one is which? So let's cut down some of the work first of all and make some observations. So first of all of these examples, if you look at this example column, all of them involve only one operation except for the distributive property, right? And you'll notice that. So all of these will tell you that they're properties of either addition or multiplication. So to keep that part straight, just look for the operation that's in the example. Is it addition or multiplication? The distributive property is not a property of addition or of multiplication because it's a property for both of those two things. That's the property that tells us how to work with both addition and multiplication in a very particular way. So it's just giving us a second option. So let's look at, we'll look at their example. 6 times 2 plus 5. So we already know one option for combining these operations, for what order to do this in. We know here that we can do, by order of operations, we can do addition first, and that would be 7, and then 6 times 7 is 42. So the distributive property is giving us a second different way to work this problem, or in other words, a second way to combine addition and multiplication within one problem. So this is telling us it's the same thing as doing 6 times 2 plus 6 times 5. And then we can verify that. 6 times 2 is 12, 6 times 5 is 30, and adding we get 42. So we can confirm that those two are the same. Alright, so that leads to another comment, which is that all of these properties are just giving us different ways to work a problem rather than doing strictly order of operations. So for example, when we see 12 plus 7 plus 3, the way that we would do this problem by order of operations is to do the parentheses first and then finish that second addition that's outside of the parentheses. So what the associative property does is just gives us another way to correctly work this problem, and it gives us justification to back up our change here, which is to do the second addition first, to do the 7 plus 3, and then go back and add the 12 after that. Right? So all of these properties are not following order of operations when you see changes like that. What about keeping these properties straight, telling the difference between them? So these might be a little bit cheesy. You may also have your own way to keep these straight, but here are some tips or things that I do to remember the meaning of these property names. So when I see commutative property, for example, I picture a commuter, maybe a commuter student. We've got that person lives at home and is commuting to school. Let's see, let's do like just a really big building for school. Put a couple different windows here, double doors. All right, so commuter student travels from home to school and from school back to home, but it's the same trip no matter which direction the student is going. All right, so commutative property tells us that 3 plus 2 going this direction is the same number as if we did 2 plus 3, which is kind of like going in the opposite direction with the addition. For the associative property, let's do like 2 plus 3 plus 1. I always picture an association like a friendship, and we would call this maybe like 3 different people, and we have like 2 and 3 are closer friends, and plus 1, that's plus 1, sort of the sidekick friend that's not as close as the best friends 2 and 3. And then perhaps the association changes maybe after a year or so, and then maybe 3 and 1 get a little bit closer and they become best friends, and then it's kind of like 2 is the third wheel out all by himself. So when you're changing the grouping or the association or the closeness of numbers, then that's the associative property. For the identity property, I always like to think about a number keeping its identity. So you want to look at what changes can be made without actually changing the value of a number. So if we had maybe like a person and we want to know, well, what are some changes we could make to this person without changing his identity? So let's say we put a baseball cap on him, right? And we would ask, is that still the same person? Of course. So obviously his identity has not changed by putting on a baseball cap. Perhaps a hairstyle changes and he grows out really long hair. Okay. Is he still the same person? Well, of course, yes. So with numbers, it's kind of the same. There are changes that we can make to numbers without actually changing their identity. So if we have the number 5, right, and we want to know, well, if I add 0 to him, does that change his identity? No, it's still the same number 5 when we add 0. And then for multiplication, if you multiply him by 1, does that change his identity? No, it's still 5, so his identity has not changed. So the identity property leads us to 2 numbers that are special because they have that property that they don't change numbers, right? So we see when you add 0, it doesn't change numbers. When you multiply by 1, it doesn't change numbers. So there's something special about 1 and 0. Okay? So when we move on to the inverse property, we're just looking at combining numbers to get those 2 special numbers. Right? So we would look at numbers that combine to equal 0, and remember we have to add 0. That's the thing that doesn't change the value of numbers. So we're looking at 2 numbers that add together to make 0. And then for the other special number 1, the identity property of multiplication, right, we multiply by 1 without changing the value of numbers. So here we're looking for 2 numbers that multiply together to be that special number 1. And then inverse sort of does have that connotation of like an opposite or like the reverse of something. So that also helps me remember what types of numbers I'm looking for. They'll either be opposite in sign to make 0, like 5 and -5, or opposite in their position in numerator or denominator, such as 2/3 and 3/2, or maybe just 2, which is really 2/1, and 1/2. Okay, so the inverse part there, it's either changing the sign or changing the fraction by flipping it upside down. So a little practice there with the inverse property. Okay, so if we had the number, let's do something interesting, the square root of 3. All right, so if you know the rules for finding inverses, if you needed to find the additive inverse here, well, the rule is still the same even though the number is no longer a nice integer. It would just be the opposite. You would change the sign on that. So the additive inverse of square root of 3 is negative square root of 3. And then what about the multiplicative inverse? Well, you still remember the same rule. You would flip the fraction, so this is really square root of 3 over 1 since we don't see a fraction. So its inverse would just be 1 over square root negative 3. Right? And that's the number that you would use to multiply times square root 3 to get the identity, the number 1. So let's step this up to something harder. What about 3 pi square root 2 divided by 6 times the number e? Okay, what would be its additive inverse? Well, this is easy. All you have to do is change the sign. So it would just be negative 3 pi square root 2 over 6 times the number e. And what do you have to do to find the multiplicative inverse? You just flip the fraction. So this would be 6e divided by 3 pi square root 2. Okay, for remembering the distributive property, I don't usually have trouble remembering this one if I think about the like what distributing actually looks like visually. So let's say there's a mom and she has 3 kids. We'll give her some curly hair here. And she's got 3 little kids and she wants to distribute cookies to them. Alright, so visually she'd be standing there with her plate of cookies. Okay? And to distribute them, maybe they're really hungry and they want to start eating right away, so maybe they wouldn't really like it if, you know, this first person got 3 cookies first while the other 2 sat there and waited for their turn. So maybe she gives 1 to each kid and then goes back and gives them some more. Right? But either way, the distributing looks like kind of splitting up those cookies and giving them to the kids, and then I kind of look at the little arrow diagram there as helpful for remembering. Now, this may not be the best example because when we distribute something like 6 times 2 plus 5, okay, you don't actually split up that 6 when you're distributing. It's actually 6 gets distributed to 2 and 6 gets distributed to 5, not just a piece of 6. So that's sort of maybe a magical world where the mom starts out with 6 cookies and every single child gets 6 cookies. Okay, so the example falls a little bit short there. For remembering the closure property, I will let the next video speak for itself. I think there's some great examples in that video to remember the closure property and what that means.